So with the concept of limit under our belt, we're going to be able to use limit to define what is sort of the central concept of the first half of calculus, and that's the concept of the derivative. And what I want to do with us is call back to the activity we did last week, where we started to think about how we use functions to model quantities of interest in decision making in business and in marketing. And we're going to use that as a way to motivate where the derivative comes from and why we would care about derivatives in calculus. So this next activity is going to get us back into the thinking about price, quantity, demand, revenue, thinking about marketing functions again, and using those ideas to dip our toe in the water to how derivatives work through the idea of what are called marginal functions. So in a minute, I'm going to turn you back into your breakout rooms to work on this activity with your small group again. But let me just prime the pump here to get us started. So how we're going to do this is we're going to think again about revenue functions. And just to remind ourselves, a revenue function is a relationship between the number of units of a product or service that we're selling. That's the X variable here, which right now I'm measuring in thousands of units. And the Y variable here is the total amount of sales revenue. So it's the amount of money that we bring in through the sales of this many units of product. So this is the same as the revenue function that we talked about last week in our activity for these Tesla bit fictitious things that we're going to market together. And so my revenue function here has the formula R of x equals minus 100x squared plus 350x. And the units of this sales revenue are in millions of dollars. Right? So what I'm going to ask you to do in your groups is to be thinking about questions today like, what happens if I'm currently producing a certain number of units and I decide that I want to change my production in one way or another? Okay? So it's a bit like saying, right now we're sitting at a certain value of x, and asking questions like, well, what's going to happen if I look at values that are nearby to that value of x? So you can see here's the connection between limits that we talked about earlier today and what we're going to talk about now. Right? And the main event here is going to be a concept called marginal revenue, where marginal revenue is an answer to the question, given how much product I'm producing right now, if I decided that I wanted to produce just one more unit of my product, what would happen? How would my sales revenue change? How much sales revenue would I bring in from selling that next one additional unit of my product? And we want to focus here on how the answer to that question actually varies depending on how much product I'm making right now. So in the beginning of this activity, I'm asking you to consider the opinion of a CEO who wants to enter the market slowly by aiming for monthly sales of 1,000 units of my Tesla bit in the beginning. So what we'd be saying is we're starting this activity thinking about the point on my revenue graph at x equals 1. Right? And then asking the question, well, what's going to happen if I decide, instead of selling 1,000 units, if I decide to increase that just a little tiny bit and sell 1,001? So if I move just a little bit to the right on this graph, what's going to happen to my revenue? First of all, is it going to go up or is it going to go down? What do you think? If we listen to our CEO and decide to produce 1,000 units of my product, that's a point on the revenue graph where if I increase production, the revenue is also going to increase because my graph looks like it's sort of going up at that point. Whereas that answer might be different if I were producing 3,000 units, and so I'm over here at this point on the graph. If I'm over here and I decide to increase my production, what's going to happen to my revenue? Yeah, my revenue is going to start going down at that point. Right? So in one of these places, we would say that the marginal revenue, the amount of sales revenue that we get by selling the very next unit that we produce, is positive. Whereas in the other case, the amount of sales revenue that I get from producing that next unit actually becomes negative, right? Because we lose sales revenue by increasing production when we're over here. We gain sales revenue when we increase production if we're over here. Right? And so the answer to that question of marginal revenue is itself going to be another function because it's going to depend on what my current level of production X is. And so in calculus, we're going to call that function an example of a derivative. Right? The derivative of the revenue function is what we're going to model as this marginal revenue function. And in some places, that derivative function is going to be positive. In some places, that derivative function is going to be negative. We want to be able to connect the properties of the original function and its graph that we're seeing on this graph right now with the properties of the graph of its derivative, which we're going to develop over the course of this activity. This activity was meant to get you a conceptual introduction to the idea of what we're going to call derivatives in calculus by thinking about marginal revenue and how marginal revenue operates. So the first things I asked you to do were to think about how revenue changes between two different points on the revenue graph. So if your CEO wants to produce 1,000 units and you think we should increase it all the way to 2,000, then there's a rate of change between those 2 points that's measured by the slope. Right? So if we increase from 1,000 to 2,000 units of production, the revenue is going to increase at a rate of $50 million of additional sales revenue for each additional 1,000 units of product sold. The slope of 50 measures the slope of that line. Whereas if I take two different points like 1,000 and 3,000 on this graph, then we're going to get a different answer for that, right? That if I increase from 1 to 3,000, then it turns out at that point we end up making less revenue at 3,000 than we did at 1,000, because, as many of you said, we're on the other side of the demand curve, right? That we're now trying to oversupply the market, and so the price that we can get for them has fallen so much that we start losing revenue after that certain point, right? And so that slope ends up being negative 50 million. For each additional 1,000 units that we sell going from 1 to 3,000, we're going to lose $50 million in sales revenue. And so all of those are questions that are answered by what are called secant lines. That's the first sort of vocabulary word here. A secant line is a line that connects two different points on the graph of a function, like the 2 points here on this revenue graph or the 2 points here on this revenue graph. But then when we start to think about marginal revenue, we start asking a question like, well, what happens if I increase production just a teeny tiny little bit, right? Instead of going from 1 to 2, what if I go from 1 to just 1.001, right? Then what's going to happen? And we find out that what happens then is that our secant line doesn't really look much like a secant line anymore, because you can barely see the two different points that it's connecting because they're so close together. And then what we get is this line that looks like it just kisses the graph in one point, right? And we call that line a tangent line. And so the first thing to know about the derivative or the marginal revenue, I'm going to use those as synonyms right now, is that the derivative, the graphical explanation of what a derivative is it's the slope of a tangent line drawn to the graph of a function. And so just by way of a picture, if I were to draw, I'm going to sketch our revenue graph on here again. So here's my function, my revenue function. And just for now, I'm going to call this function f of x instead of r of x. And then we pick a certain point on the x-axis. I'm going to call it x equals a instead of x equals 1. Right? And so there's a point on the graph right here at a y value that we call f of a. But then if I draw a line that just barely kisses this graph at that one point, then that line is called a tangent line to the graph. Tangent means it just touches at the one point instead of connecting two different points. And the slope is called the derivative. Or if it's marginal function, we call it a marginal derivative. It's the derivative of the function of f at the point x equals a. And the reason that we talked about limits in the beginning of today's class is that we sort of need the concept of a limit to even be able to talk about where a derivative comes from. Because we need the 2 points that we're choosing to be so close together that really we can only define it by letting one point approach the other point, right? So that's kind of what you were doing in this manipulative here in number 6. Where in order to figure out what the marginal revenue was, we didn't really want to pick two different points on the graph that are really far apart. We wanted the second point that we pick to be super, super close to the first one, right? And so as that second point approaches the first point, the slopes of those secant lines are going to approach a number that we call the derivative. And the closer that the second point gets to the first point, the closer that that slope number gets to the slope of the tangent line. And one of you said in your groups when we were doing this number that we got for the slope looks like it's roughly 150. And the reason it's roughly 150 is that the actual slope of the actual tangent line at that point is actually 150. And so the derivative is what we get by finding the slope of just that tangent line. Whoops, and I just realized that I wasn't showing you my screen like I thought I was. Let me try that one more time. So the slope of the tangent line is the slope that we get as that second point approaches the first point. And we compute the slopes of the lines on the graph as that second point gets arbitrarily closer to the first one. And on this graph, the closer that my second point gets to my first point, the more that that slope starts to look like the number 150, right? And so the number 150 actually is the slope of that tangent line to the graph. And another name for the slope of a tangent line is it's the derivative of this function at the point x equals 1. So in our example, we would write if f of x is negative 100 x squared plus 350x, this is my revenue function, right? Then we would say the slope of this tangent line is what we would call f, with a little apostrophe up here, f prime. This is what we write when we want to say derivative of f. It's the same as the slope of the tangent line. And if I were to evaluate this derivative at the point x equals 1, right, so this 1 right there is my a, my x value, where I've drawn this tangent line, then we would say that f prime of 1 is equal to 150. It's the slope of that tangent line. And so what we notice in this activity is that since we know that the derivative, if we agree that the derivative is the slope of a tangent line, then the derivative is evidently going to be positive in some places, like over here on the left-hand side of my graph. It's going to be negative in other places, over here on the right-hand side of this particular graph. And there also is a place on this graph where it looks like this slope is roughly 0. I can't quite get to it here because my point is kind of skipping to either side of it. But there's a place where this slope becomes 0. And that place turns out to be the top of the revenue hill. Right? Hang on to that observation for next class meeting in 3 weeks, because that is the secret sauce to how we use calculus to do optimization problems, how to find the maximum of something or the minimum of something. The first places we look are the places where my graph is not increasing and my graph is not decreasing, but that my graph has leveled off. And it's leveled off when the slope of a tangent line is 0. And if the derivative is the slope of a tangent line, as we say it is, then those are going to be the places where the derivative is 0. So I'm going to put that in my verbal description over here. That one of the most important ways that we use a derivative is to intuit the properties that a function has. So if my function f is increasing, then the derivative, f prime, is positive. So in our example, that would be the left-hand side of this graph. So everywhere here where my revenue function is increasing from left to right, all of my slopes of my tangent lines are positive numbers. My derivative is always positive over here on this side of the graph. Conversely, wherever my function is decreasing, so wherever its graph is going down as we go from left to right, my derivative, the slopes of its tangent lines, are going to be negative. So there, we're describing the right-hand side of this graph. Here, my function is decreasing, my red curve is decreasing, and so the slopes of its tangent lines all come out to be negative numbers. So where my function is decreasing, my derivative is negative. And so if I'm at a place where neither one of those two things is true, where my function is neither increasing nor decreasing, so is what we would call, well, I'm just going to write the word neither. Neither increasing nor decreasing. Sometimes we call that a stationary point. And that's going to be a place where my derivative is neither positive nor negative. But really, as long as my derivative is a number, there's only one number that is neither positive nor negative. And that's 0. And again, this is an observation that we're going to want to hang on to for next class meeting, because that is how we're going to be able to use derivatives as a way of getting at one of the most important properties that we could think about for a business function, which is where does this function reach its maximum, where does it reach its minimum? It's going to happen at a place where the function is neither increasing nor decreasing. In other words, a place where the derivative is equal to 0. So the last thing that I want to do before we wrap up, I know I'm borrowing a few extra minutes of your time, so thank you for indulging this last point, is I want to go back to the algebraic context up here and ask the question, well, how could we have gotten this number, 150, without using a graph, without using technology, without using the numerical viewpoint to approximate the slope of this tangent line? How could we have gotten that number using the formula for f of x? And so for that, I'm going to give you just the rule of thumb here. And the rule of thumb is called the power rule. It's what tells us how to take the derivative of any function whose algebraic formula is built out of powers of x. Power rule. And the power rule says the following. It says that the derivative of a function which is x to some power, the derivative of, I'm going to write it here, the derivative of f of x equals x to the power r. The derivative of the function x to the power r is obtained by doing a two-step process. I like to think of it as a two-step process. The first process is we multiply my formula by the old exponent, r. And the second part of the process is we will decrease the exponent by 1, so that the new exponent is r minus 1. F prime of x equals r times x to the r minus 1. So this is the little sort of shortcut. Right? It's how we can turn a formula for an original function into a formula that lets us compute its derivative. Okay. So let's apply that to this example, and we'll use this to wrap up today. How could I have known that the slope of this tangent line was 150, as we said it was in the activity? I'm going to zoom in on this just to make sure that we're all able to read this. So what I would do is I would look at this formula, minus 100x squared plus 350x. And I would first try to find the way in which this formula is built out of powers of x. And I can see two powers of x that are building blocks in this function. I've got a power of x right there, and I've got a power of x right there. Right? I've got an x to the power 2, and I also have this plane x here, which, according to properties of exponents, is another name for x to the power 1. Right? So I have these two powers of x, and these two powers of x are glued together into this formula by multiplying them by numbers and by adding the results together. And the good thing about derivatives is that the linearity property of derivatives lets us take the derivatives of just these individual pieces and then knit them back together in the same way that they were knitted together in the first place. In other words, I'm going to use this power rule to take the derivative of this x to the power 2 and to take this derivative of x to the power 1, and then I'm going to put all the pieces back together in the same way that they were. So for x to the power 2, according to this process, I want to do two things. I want to first multiply by that exponent. So take the 2 and multiply down in the front. And then the second thing I wanted to do was to decrease that exponent by 1. And so my new exponent becomes an exponent of 1 for that piece. And then I still have my negative 100 that's out in the front of that. I'm computing the derivative now. So for my first term in my derivative, I get negative 100 times 2 times x to the power 1, according to this power rule applied to x to the power 2. Then I'll do the same thing for the second building block, x to the power 1. We would start by bringing the exponent of 1 and multiplying it out on the front, 1 times, and then decreasing that exponent by 1, so that my new exponent is x to the power 0. And then I'll have my 350 out in the front of that. So there is an application of the power rule. All I want to do now is kind of clean up this expression just so it's easier to work with. X to the power 1 is another name for just plain x. And so when I simplify this first term, negative 100 times 2 times x, I'm just going to get negative 200x. in my second term, 350 times 1 times x to the power 0. Well, to raise a real number, a non-zero real number, to the 0th power is to turn it into the constant 1. X to the power 0 is equal to 1. So this x to the 0 is just going to become a factor of 1. And then I have 350 times 1 times 1, which simplifies out to just 350. So at the end of this process, I now have a derivative function, f prime of x equals negative 200x plus 350. There's my derivative for this. And so if I wanted to know, for example, what is f prime of 1, I would just evaluate that derivative function. Let's make sure that this works. The slope is f prime of 1, which according to my new formula for f prime is negative 200 times 1 plus 350. And when I simplify that out, I get negative 200 plus 350, that's 150. Which is what we hoped it was going to be. Right? But the real benefit of this is now that we can see the derivative as a function in its own right. And we can graph that derivative as a function in its own right. And this was the last question on this activity, which let's use this as a way to wrap up. So let me move back over to my browser screen here. So the last thing I asked you to do was to point out which one of these colored graphs would seem to be a graph of the derivative, the marginal revenue function. And so the key here, and it's what I had on my screen just a minute ago. I'm going to put it back up one more time. The key here is this verbal description of the relationship between a function's properties and its derivative's properties. We're going to be looking for a derivative function which is positive wherever my function is increasing, and which is negative wherever my function is decreasing. So my revenue function is increasing everywhere to the left of the top of the hill, everywhere from 0 to about 1 3/4. And so everywhere that my revenue is increasing, I need my derivative to be positive. In other words, I need my derivative function to be above the x-axis. My red, purple, and green curves are all above the x-axis for this part of my revenue graph. But my blue curve is not, so I have to rule out my blue curve. Can't be this one. Right? Because I need the derivative to be positive, in other words, north of the x-axis, wherever my original function is increasing, going upwards. Similarly, I need my derivative function to be negative, needs to be south of the x-axis, whenever my original function is decreasing, going downward on the graph. My revenue function is going downward over here on the right-hand side of my curve. Right? And so I need my derivative function to be south of the x-axis for those points. And there's only one graph remaining which does that, because this blue curve is north. The blue curve is positive where the revenue function is decreasing. This green curve is positive where the revenue function is decreasing. And the purple curve is positive where the revenue function is decreasing. The only one which is negative, south of the x-axis, where my revenue function is decreasing, is my red curve. And so my red curve is a graph of the derivative of my revenue function here, because it's positive north of the x-axis where my revenue function is increasing, and it's negative south of the x-axis where my revenue function is decreasing. And sure enough, if we think about the formula that we came up with for this derivative function, f of x equals negative 200x plus 350, that, if we were to graph it, is legitimately the graph of a decreasing line. Right? And so if I graph, well, let me do this on the screen here real quick. Here's my original function. The graph of my derivative function would be that decreasing line. F of x and the derivative of f of x. So that kind of gives us the full range of perspectives on what the derivative is, and the marginal revenue activity kind of gives us a rationale for why we would care about the derivative of a function that we talk about in a business context so far. So what your work this week is going to involve, sorry, let me get my camera camera set up here. What your work this week is going to involve doing is thinking again about limits and computing limits from these various perspectives, and then also computing derivatives of functions which are built out of powers of x. And this gives you the introduction to kind of what they are, how we can think about them in different ways, and a little bit about how to compute them. As you get later on towards the later topics, we'll have a little bit more complicated functions to compute derivatives of using algebra, and so there's some new rules that come in, a rule for products of functions, and a rule for compositions of functions called the chain rule. I'll share out some resources on those. They're really sort of nuts and boltsy at that point, and I wanted to make sure that we used our time together to talk about the bigger ideas, which I think we got a chance to do today.